the 9th, 2001, Saturday at 10 a.m. We're at the home of Dr. Jack Schubert, Professor Dr. Schubert. He has served in teaching positions in several countries, as well as with me at the School of Public Health in the 60s and early 70s at the University of Pittsburgh. This is Alan Brodsky. I'm conducting this interview for the History Committee of the Health Physics Society with the permission and approval of Sid Porter, chairman of the committee. We are interviewing Jack Schubert because he has had an almost 60-year illustrious career as a chemist and health physicist, and is studied in many different areas that are applicable to the safe uses of radiation and its byproducts. And so I'm taking this opportunity at his kind invitation to his home. Now we will start out by asking Jack, well, you might as well start from the beginning. That's one way to organize one of these. Can you remember the people who may have influenced you as you grew through your life, and how you came to decide that you really wanted to go to college, that you wanted to study science? Just the things that you can recollect naturally. The most important things will come to mind, I'm sure.
Well, I was always interested in math and science, and I had a very good chemistry teacher in high school. I still remember his name, Grinstead. And that influenced me to consider going into chemistry. And when I graduated from high school, I actually wanted to go to college, but I had no money, and I had to really contribute money at home. But I won a competitive scholarship, but I gave it up after a half year because I couldn't afford the 7-cent car fare to get there, or any of the books. There were no particular student help at that time. So I switched to going to college at night.
Both at the University of Chicago?
Well, University of Chicago, but also, in order to get a degree in 4 years, it's impossible to get a degree in 4 years in science, especially going at night, because they limited you to 1.5 courses a semester or a quarter, like at the University of Chicago. So what I did, I took courses at a couple other places, and then I would send the credits in to the University of Chicago. So I attended Northwestern University at night. I attended what was called the Central YMCA College. And in that way, I eventually got my degree by taking full load at night.
You actually got your degree in 4 years?
Yes, I got my degree in 4 years, and I didn't even go summers. I worked summers.
You must have been an excellent student to do all that.
Well, it was tough. And then I was working full-time while going to college at night, so this was rather difficult. And especially taking courses like calculus and partial differential equations, chemistry, physics, all those kind of courses. And going at night, I didn't have access to a laboratory to work in. I had to do analytical chemistry. But fortunately, a friend of mine introduced me to a professor at DePaul University. He was a Catholic priest, but he kindly let me use his laboratory on weekends, so I did my experiments there. And going to school at nights, living in the north side of Chicago, and going to the University of Chicago at night, which was on the south side, meant going an hour at least on the L trains between the University of Chicago and my home. And this sometimes meant leaving at 10, 11, midnight, and getting up early to do my work, regular work. The one thing I do remember about going to school at night was I took a course in calculus and physics. It was given at the same time. They were Monday, Wednesday, and Friday evening, as I remember, 6 to 8 in the evening. And I managed to alternate. So sometimes the physics professor would say, "Where have you been?" I'd start going to his class. And then the math professor would say, "Where have you been, Schubert?" So I go to his. Well, I managed that until the finals, which came on the same night, same time, 6 to 8. And I had a debate, which one should I take first? Well, I wasn't doing too well in physics. No, I was doing okay on the physics, but in laboratory I wasn't there much, and this was a detriment. So I took the physics exam. Unfortunately, it took me the whole 2 hours, and I ran up to the math professor for my calculus exam. I was doing much better in math, of course, since there was no laboratory. And he was getting ready to leave, and I ran up there, and I remember him saying to me, he was a nice guy, his name was Greenville Dorr. He said, I told him I had to take the physics exam. I think he knew something about it. He said, "Well, I guess you're more afraid of Dr. So-and-so in physics than of me." Anyway, he gave me the exam, put me in his office, brought me a Coke, and left. He said, "Leave the exam." And which was very nice. Well, then, I also worked a good part of the time while going to college at the Sargent Company, chemical suppliers on North Michigan Avenue in Chicago. And they, I would fill orders for chemicals and apparatus or assemble things, and which was sort of chemically related. Anyway, I did get my degree, bachelor's degree in 1940, in the regular four-year stretch. And actually my grades weren't all straight A's by any means because of these working conditions. And sometimes I'd work until 12, 1 in the morning, and then get up at 5 or 6 and try to do my homework, part of it on the L train and wherever else I could squeeze.
I didn't get all that high grades in chemical engineering, and I was full-time.
Yeah. Anyway, I got my degree, and actually I majored in physical chemistry and minored in biochem and math. Well, then graduate school was practically out of the question because I had no money. As a matter of fact, so short of money that some of my fellow students in evening classes at the college offered to buy me a pair of pants or stuff like that, which I turned down. Well, then I applied for a job. There was a job advertised at Burgess Battery Company in Freeport, Illinois, which was about an hour and a half, 2 hours by train from Chicago. And at that time, they were offering a very good salary. I mean, $125 a month, which was offered by the big companies for bachelor's degrees, like DuPont and so on. Well, it turned out that they were wanting to set up a department, chemistry research department. And I went for the interview at the Stevens Hotel in Chicago. There were loads of guys. And I remember going into the interview, there was this man who happened to be director of the labs there at Burgess, sitting behind a table, and I sat there and started asking me questions about Ampere's law and laws of thermodynamics and all those kind of things, which I answered refreshing after my bachelor's degree. I got the job, and that meant going to Freeport, Illinois, renting a room at the local YMCA. And prices were cheap then, of course. A steak dinner with all the trimmings was 55 cents. But anyway, so I went there, and the first thing I was confronted with was sort of an intelligence exam. Meantime, they hired X-ray crystallographer from the University of Illinois, I don't recall his name, as the head of their research. They wanted to set up a real upgrade research. That's why they were paying the salary of $125. And so I took the exam, And I think they considered me a genius there because I made the highest score I ever had, even much higher than the X-ray crystallographers. Way higher. Well, I was there at least 6 months. That was in 1940. And the work I did at Burns was an interesting way. They were making dry cells. You use carbon black, which they call Schubert Black, which was made from decomposition of acetylene, which produced a very fluffy type of carbon. Now the dry cells, uniformity wasn't always good, taken off the assembly line. So I decided to see if I could make it more uniform. So the thing I did was to measure the surface area of the carbon black batches using iodine absorption, and that, knowing the dimensions, I did not calculate the surface area. Part of this was because I took a course in surface chemistry with Dr. George Boyd, who was a new member, assistant professor of surface chemistry at the University of Chicago. And so I started doing research for a master's degree, because I didn't think I'd have any chance to ever go through for a doctorate. And I was working on surface chemistry, surface thermodynamics.
Also at the University of Chicago.
University of Chicago. But I did the research at night. I would commute from Freeport, Illinois, and then work until 2, 3 in the morning.
Wow.
Doing the measurements.
Wow. What a strong hit.
Surface energies on monomolecular films. It worked out very interesting. We published a paper on it, showing certain changes as a result of pressure and temperature. And well, I commuted there for about, I'm not sure, I was in Freeport, Illinois, Burns for 6 months or close to a year. In the meantime, the military draft was hitting me. I got the ferments because I was supporting my mother and that. And so they gave me this called family deferment. But as the war continued, things got tougher.
You mean the war started already by then?
Pardon?
World War II had started?
Yes.
You graduated 40.
No, World War II started, well, in December 41.
And you were talking about that time now?
Yes. And
you'd already been working then while the war
I was working for Burgess Battery, but I knew my time there would not be long. I kept getting draft deferments, but I knew they were going to end. And I took civil service exams in meteorology and in chemistry. I was called for both, so I could have been a meteorologist, but I took the chemistry job. That was at the Charlestown Ordnance Works, run by DuPont, Charlestown, Indiana, across the river from Louisville, Kentucky. And I went to work in the smokeless powder plant, analyzing smokeless powder from all sorts of cannons and aircraft, anti-aircraft, and so on. There were 3 ships, which was very difficult. And so I worked there, and even then the deferments were getting tighter and tighter, even though I was working for a fencing.
Were you far from your mother, far from home if they were working there? Or did you live at home when you worked there? Did you live at home with your mom when you worked there?
No, I was living in Louisville, Kentucky.
Louisville, Kentucky.
My mother was living in the north side of Chicago. My younger brother was home for a while, but
so he helped out, huh?
well, no, he wasn't working, but I helped out, and my mother's family helped her a little bit with rent or something. And I'd send her money every week. And then I got a letter from this Dr. Boyd, with whom I was doing this surface chemistry research. And I got a telegram saying that some project and would like me to join it. It was very secret, highly secret. This was in '41, before Pearl Harbor. But he also said, not in a telegram, but I think in writing or talking with me, said I'll be able to use any research I do maybe for a PhD. Well, for a guy who never thought of getting a PhD, because remember, there was no student assistance and I had no money to work full-time. PhD was not something you do only at nights. So I said, sure. So came back to Chicago, University of Chicago, which was a metallurgical project. Its primary aim was to build a reactor, which Fermi did at that time. That was University of Chicago. And my primary, the group I was in was analytical chemistry of uranium and other products related to purification of uranium and so on.
Yeah, so you published a paper, I noticed, in your
Well,
book of papers.
well, that was
separating fission products from uranium.
yes. Well, that was later on. My primary job was to do analytical work. And I did analyses on uranium. And one of the cases was to purify it by extraction with water from ethyl alcohol. Ether, regular ether, which uranium nitrate is soluble in. And then you extract with water, which took out most of the fission products.
Where did you get your methodology, your literature?
That was a standard methodology, well known. I think Mallinckrodt chemical was originated. And there was some military man, I forget his name, who supervised and overall his responsibility. And, well, it was a pretty good thing, but rather interesting thing came up. I forget the name of the person, but I have it in a notebook I written, which is now in possession of the AAC. This fellow made a simple suggestion. So instead of extracting with water, which you keep losing uranium, he says, use a uranium solution instead of pure water, a water solution of uranium, and then extract. And that worked very well. You didn't lose any uranium from the other solution. Well, this seemed like a simple matter. I wrote it up, kept a pretty good notebook then. This became a matter of, quite a matter of importance, because a couple of the project leaders in the Manhattan Project were claiming credit for this simple procedure, extracting with uranium nitrate in water rather than just plain water. Well, when my notebook came to the attention, that ended, because it was clear who was and who the guy was and when he was. And one of my first experiences with credit claiming by people. And anyway, and then I thought of a better way, especially based on my experience in surface chemistry and the absorption work I did at Burgess Battery. I decided to see if I could purify uranium by absorption. And so I used absorbents like Fuller's Earth, bentonite, inorganic absorbents. It worked quite well. I have a couple reports which I should publish. I think it should be published in Health Physics because they're very important. I have to retrieve those papers to the AEC in Washington, D.C. And then George Boyd, professor who was head of the analytical thing that I was working in, he recommended using an organic ion exchanger, Amberlite IR1, which was a new thing, which he had a sample of given to him by Professor Harkins, a very well-known nuclear chemist and surface chemist, with whom George Boyd actually worked and got his degree. So I used the Amberlite, and I found that, gee, it worked very well. I could run a solution of uranium nitrate, water solution, through the ion exchanger in the sodium form or uranium form, and it would take up the uranium would run through once the uranium resin was saturated and absorbed no more uranium. The uranium would run through, and all the thorium, which was standard for plutonium, was absorbed completely. thorium being a tetravalent thing, far very strong. Seemed like an ideal thing for the separations. I published a report on the project on that too. And that led to the development of ion exchange as a process.
All this was while you were working on your PhD?
Yes, well, I was working on whatever would come along with the PhD, but I wasn't working, I was doing specific applied things.
Yeah.
And
While you were taking your courses too, I guess.
oh yeah, I would commute during the war, especially between Oak Ridge and Chicago, which was very difficult during the wartime. The commuting was because I was taking courses in Chicago, but I couldn't attend the lectures, but I had to come in for the exams. So some more commuting, and that was pretty difficult during the war. I didn't have much money.
You had to go to Oak Ridge to do your work, is that it?
Well, no, that this work was done at Chicago, I'm talking about.
Because you said you commuted from Oak Ridge.
Well, that's later. When the ion exchange process worked up to be quite successful, we studied it. There were several members in the group who joined, and one of the things I did was to get rid of the uranium without getting rid of the thorium by using complexing agents, sulfuric acid, which was easily remove the uranium but didn't touch the thorium. Then we got some very weak samples of plutonium from the Washington University reactor. I mean, we're talking, counts per minute, not millions of counts. But we had pretty good counters. We had people in the setting up the Geigers net were very well known. Some became the original Packard company, and so on. Very good people. And so I used plutonium, and then the group went over and used plutonium, and we found that it worked pretty much like thorium. And then this led to the development, which I wrote up in a big review article with George Boyd on the first use of ion exchange in the Manhattan Project.
Was that secret at the time? Secret?
Yes, everything was secret, top secret. As a matter of fact, you mentioned top secret. I think I mentioned to you. One time I went to the library in Chicago, this was still Chicago, and requested a report that I wanted to read or look at. The librarian said, "You can't have it, your clearance isn't high enough." I said, "But I wrote the report." So they actually changed the rule that any report you've written, you can get out regardless of your clearance. And well, anyway, that's a big detailed thing of what happened and how it developed. And eventually the ion exchange procedure also was used to isolate and identify several of the transuranic elements that came later. Anyway, the ion exchange worked up to practically a pilot plant level. We had all the things worked out pretty well. And so then we moved to Oak Ridge.
Was it after you got your doctorate you moved to Oak Ridge?
No, that was later. I didn't get my doctorate until 44. This was in 41.
Was the subject ion exchange for your doctorate?
That was one of them, yes. Ion exchange was the main one for my thesis, yes.
And you wrote a book, I see, as co-author.
I didn't write a book, I edited a book on ion exchange. Ion exchange technology at the time, but that was much later. Anyway, but while at Chicago, they were having a problem with the purity of uranium that Fermi was using in the pile. The uranium was made by a company called Metal Hydrides in Beverly, Massachusetts. And they made the uranium metal by using uranium powder and sintering it, heating it under high pressure to make the metal. Well, that's a dangerous procedure because powdered uranium is very pyrophoric. But anyway, the main thing was there were still too many neutron-absorbing impurities in that uranium. So I was sent to set up some microanalytical procedures for neutron-absorbing impurities in uranium. So first I went to the Bureau standards where Robin, who was an important factor in the Manhattan Project, analytical chemistry.
Is that R-O-D-I-N?
Yeah. R-O-D-D-E-N.
DDEN.
And then from there I went to MIT, where this other fellow was setting up microanalytical procedures and analyzing.
You mean just visiting there, you mean?
I was visiting there. And then, after getting all the information, I ordered equipment, and I set up the microanalytical lab at the Beverly Hydrides plant where they're making the uranium to analyze for neutron-absorbing impurities. And now eventually, Spedding at Ames, Iowa made a very, using ion exchange, they would purify uranium and make a metal. They had metallurgical department. Really good, solid metal, not this pyrophoric stuff. And eventually that became the standard. I don't recall whether Fermi used any of that. That may have come later, so I guess he used this uranium from metal hydrides for this stuff. Unfortunately, when the pile went critical with Fermi in September, I was in Massachusetts, microanalytical. Anyway, I came back, and then shortly after, we went to Oak Ridge for a year and a half to set up a pilot plant level for ion exchange processing of uranium, separating from fission products and plutonium and so on. And that meant scaling up to pilot plant level, which we did.
Fermi stayed in Chicago, I guess, huh?
No, the pilot plant was set up in Oak Ridge.
I mean, Fermi didn't go with you, did he?
Although he had nothing to do with that.
Nothing to do with that chemistry.
Yeah, this was straight chemistry. However, I met a lot of people at Chicago. I mean, there was...
You knew Fermi, didn't you?
Pardon?
You knew Fermi. You knew Fermi personally?
Yes. Fermi, and then Arthur Compton was the overall head of the metallurgical lab of Chicago. And as a matter of fact, I would have... Speaking of that, when I joined the Manhattan Project, I got greetings from my draft board to report. Fortunately, Compton and General Groves wrote a letter on my behalf to the draft board, so I remained on the Manhattan Project.
You knew Compton well?
Oh, very well. Well, he was, professor of physics there.
What was he like? Can you remember?
In what sense?
What personality?
Oh, he was a very nice, personable, tall, very handsome man. And he worked, along with Fermi and Compton and Conan, the big people in charge overall of Manhattan. Remember, we were sort of compartmented. Even at Oak Ridge, there were 3 different units on preparing uranium. One of them involved making uranium hexafluoride. The other was the isotope separations.
You had worked on that too, huh?
I didn't work on that.
Oh.
But that was Harold Urey, another Nobel Prize. He taught statistical thermodynamics at Chicago. And at Chicago, I got to know James Franck quite well. And there were several, and then Seaborg, I got to know Seaborg very well. As a matter of fact, he asked me to introduce one of his radiochemists to the absorption procedures I was applying. So I worked a bit with John Willard, who's chemistry professor, assistant professor at the University of Wisconsin, and introduced him to the absorption procedures that I was using. And Seaborg's group. We had other minor technical problems. We had a meeting once where trying to figure out why the uranium readings on the platinum disc were higher than they were expected for the amount of plutonium on the disc. About 2% higher. Well, a lot of thoughts came up, but nothing specific. But then eventually it turned out that the platinum was reflecting some of the alpha particles from plutonium and giving higher than expected readings. So that was important in the calibration. There were a lot of other problems with that stuff that were eventually solved. Anyway, so I went to Oak Ridge for a year and a half with the group. A lot of people came very well. Arthur Adamson, who became very well known as a surface chemist, and the book on surface chemistry is the standard text in physical chemistry as well. Chemistry. And then there was Lawrence Myers and Wexler, Mata. A bunch of people, right? Anyway, at Oak Ridge, we set up large ion exchangers. We had a walk, catwalk, and had big columns. And
Well, after this break, we'll resume. Of course, you know, this is just highlights. Jack's 60-year career with so much accomplishment and several books is impossible to cover even in a couple of hours. We're going to give this interview more time than usual because there's a very long career here that's worth recording. So I'll let you continue then, Jack.
well, at the metallurgical lab in Chicago, I should mention that there were two main groups aside from the physics in the reactor group. Was the fission product chemistry group, which was headed by Charles Coriell.
Know that name.
And as a matter of fact, two of his people, Lawrence Glendenin and
Another name. All big people.
and Ellis Steinberg discovered element 61 while Coriell was a very nice man, brilliant guy. He worked with Pauling for his thesis, and very brilliant, very nice guy. And one of the interesting things was I developed an equation for measuring stability complex ions where you can measure as many elements as have radioactivity with no chemical amounts present to measure stabilities using ion exchange technique, which is sometimes referred to as the Schubert method. And I use that to measure stability constants of radium and other elements. And the equations I developed, I showed it to Charles Coriell. He pointed out one modification. Oh, I said, you should know. I said, Jack, you should know that ever since you were knee-high to Glenn Seymour. I said, Charles, I'm still knee-high to Glenn. And anyway, to get back to Oak Ridge, we set up these
You still haven't got your doctorate yet?
No.
At this point?
No, not at all. We're still talking about 41 and 42.
Oh, so
You're
you're not even writing your doctorate?
I got my bachelor's in 40. I couldn't have got it back.
So you didn't even start writing your doctorate yet?
No. No, I was still a graduate student. And commuting between Oak Ridge by train during the war periods with scarcely a seat in the train, GIs all over the place. I remember coming back this one day from arriving in Chicago. And there were big headlines of paper, Japs bombed Pearl Harbor, so it was December 7th, 1941. And all of us knew in Chicago, when I got there, we were all listening to President Roosevelt's talk about declaring war on Japan. We all sat there in the Jones Chemistry Building, and all graduate students and faculty and everyone listening to the talk. Anyway, that's a sidelight. And I should say, we used to get our uranium oxide from the Congo, actually. We had a lot of it that the government had bought. And one time, I tried to dissolve it, as usual, in nitric acid. It wouldn't dissolve. I didn't know what was wrong. It was nice black uranium oxide. So, this consultant, a retired chemist who was very experienced on rare earths chemistry, he worked for Lindsay Chemicals, I believe. Herbert McCoy, very nice man. And he looked at the stuff. We had them in big silica dishes. And he added some hydrogen peroxide, and it seems to work. When he left, it still was dissolved. It turned out that someone had given us by mistake carbon black instead of uranium oxide. One of the little things that come across.
Now this, so the project you were working on actually in Chicago, it was a result of this letter from Einstein, written I think by Szilard for Einstein to the president. I believe it was Szilard who wrote
Yes, well that started in Manhattan.
and that started the Manhattan. So actually before we were at war, declared war with Germany and Japan, actually President Roosevelt recognized that we might need that atom bomb.
That's right.
Eventually.
And
Because
that's why we were able to
he
get-
felt Hitler probably was working on it, right?
Well, that's what we thought. And that's
But
why...
you didn't know you were working on an atom bomb yet at that time, did you?
Yeah,
You knew from the beginning?
pretty well. Yeah. There was a book by a guy, Jack Dement, on uranium and the bomb and everything.
Oh, really? Back
Yeah.
then? Huh?
Talked about an atom bomb.
Uh-huh.
But,
Unclassified book.
pardon?
An unclassified book, huh?
Yeah. Anyway, all this stuff was mobilized by the government well before the war with Japan and Germany. And I was well into working on the plutonium separation and all that before Pearl Harbor. At Oak Ridge now, on the pilot plant, we ran into one problem. We put the solution through and all the uranium and plutonium ran right through the column. Couldn't figure out what's going on. Well, the work we did in Chicago was with glass columns, where we used big metal columns for pilot plant work. And what had happened, the uranium resin with uranium, by that time we used a better quality organic ion exchanger made by Dow. We found that uranium surface chemistry, uranium resin was such that it pulled away from the walls of the metal column. And so you had an opening, annular opening, which the solution ran right through. Because we used to measure breakthrough and so on for calculation. Well, we realized that the columns had to be glass lined, otherwise we wouldn't.
It's interesting.
Well, that's typical pilot plant work. You run into unexpected things. You have to deal with it. And in the meantime, I was also working on developing fundamental methods of ion exchange and measuring complex ions with it, measuring the nature of the absorptions of functions, valence, charge, and chemistry of the ion. Eventually, I ended up with 7 patents on the ion exchange processes, of which on the first 4 I got $1 for each patent. Later on, I think I might have gotten, the last 3, I might have gotten $25.
No royalties, though.
And, well, anyway, so the work on ion exchanges, a lot of it was fundamental. And Adamson did some very nice work on the kinetics of ion exchange absorption. And we also worked on different absorbents like zirconium oxide and so on, which Ed Russell, I should mention, also worked on the absorption process. We had several people developing it. And so eventually I was able to put together enough material, which I wrote up as a report, which was the basis of my thesis. And, well, in order to be admitted to PhD research at the University of We had to pass satisfactorily 4 3-hour exams in 4 different fields of chemistry. This was over a 2-day period. And then if you did well enough, you were admitted to the orals. If you did very well on the written, but they thought wasn't suitable enough for a PhD, they allowed you to take a master's degree, and then you have to leave. I mean, nowadays that would never happen. But, so that's why those of us
it's easier now, you mean?
Pardon?
I mean, nowadays it's easier, you mean?
Maybe not easier, but I mean, they're not that restricted, or may give you more of a chance.
Mm-hmm.
Because, you know, you don't want to lose students. There was one fellow I remember, in all the graduate courses I took, which were extra physical chemistry and graduate course in thermodynamics and more math and all these things. There's one guy, absolute grades, perfect. I never saw any guy that did so well on the exam. He never could pass the written orals, get into it. He eventually did get a degree. He went to another university. But it was amazing. Anyway, I guess he couldn't put it together. On an individual exam, it would be great to integrate it all. Anyway, so I took the writtens at Oak Ridge under Arthur Adamson and I both took it under Boyd's supervision. And we both passed it, and then we had to take the orals. On the orals, we had a very good committee. There was James Strong, Herbert Johnson, the inorganic chemist, George Whelan, the quantum organic chemist, and statistical thermodynamics fellow, I don't quite recall his name now. And I had trouble with the organic chemistry part. I never liked to memorize stuff, and, you know, at that time, but I was pretty well versed, but I didn't study the organic nitrogen compounds. And they hit me on that, they wouldn't let go. So I had to repeat that, which I did. There's a myth to that. And eventually took the finals. Adamson and I both passed that, and both got our PhDs in 44. Then,
pretty good in 4 years.
And
that's all you did.
And then I left Oak Ridge in March of 45, go back to Argonne, where I resumed working on radiation chemistry, and I also switched into biological subjects, like plutonium. We moved into plutonium. And many other aspects of that. So, my CV will show you.
Is that when you started doing the research on animals?
Yes.
And the uptake of plutonium and the physiology and chemistry? That's when you
I
started that?
I eventually got into radio protection, radiation chemistry at sewage. And
when were you called upon to set up the bioassay laboratory there?
when I returned from Oak Ridge,
In
March of 45.
45. And that was one of your duties immediately?
Yeah, that was one of my responsibilities.
Until then, they had no urine sampling or anything?
They did do urine sample, but it wasn't, they only had, the number of analyses that was limited, and with Larry Myers, who worked with me, we set up analyses for many of the other fission products. Not always original. Well, I did make some modifications in radium analyses, but we set up analyses for plutonium and fission products and so on.
Had they been doing good plutonium before then?
On plutonium before then?
Yeah.
I worked with plutonium all the time as a Manhattan.
No, but I mean, did they do urine analysis on people?
No, I didn't do urine analyses, but I...
Did anybody before that time? Did Oak Ridge, they have for plutonium urine analysis?
I don't know
for
what the
workers?
other groups were doing. There were the biomedical group, there was a big group at Rochester, University of Rochester.
Yeah.
And there were the Bureau standards and the ROD set up. There was a lot of analytical work going on.
But you don't remember submitting urine samples before plutonium, before that? So,
I think we did set up, we did some
Did some monitoring.
urine sample. Actually, the man in charge of the biomedical stuff at Chicago was Nixon, N-I-C-K-S-O-N. He was a medical doctor. And as a matter of fact, the results were published in a series of AEC publications, or books. And that's all written up in there. And I wrote a chapter or so on that too. I also developed
those blue books, the
Yeah,
series,
blue
the National Nuclear Energy Series.
That's right.
Right.
That's all written up.
In there.
And I developed some ion exchange methods for isolating yttrium from urine. I set up methods for isolating things from urine, as a matter of fact.
So your name is in those books then, I guess.
Yeah, I have a chapter in there. At least one I remember, because I have to look at my CV.
Yeah, I know what you mean.
And,
Well, take that. I think we'll take a break. Okay, we'll resume.
well, I returned to Chicago to the Argonne lab and worked on methods for chelation removal of plutonium from animals, hoping it would have human application. I set up the bioassay group, and we published that as a report of the methods we used.
I used to give out to the students those 3 papers in nucleonics were kind of seminal, where you
Yes.
described a lot of the theory of bioassay
Yes.
for various nuclides. It was very comprehensive,
But the specifics
interesting
of
papers.
the analytical procedures were published at the Met Lab. There's a report number.
Yes, but for general education of the profession, I imagine your papers might have been, in nucleonics, might have been the first.
It might have been, there were
I don't know about the
papers.
others.
Yes, they paid, nucleonics paid.
Yeah, they paid me once for a little bit.
Yeah, and which was helpful because that helped pay for the birth of my first child. And then Scientific American paid for the birth of the second, and also for the third. Helped because we didn't have much money. And it's a good thing if they weren't paying more money, I might have had an infinite number of kids. But anyway, in when was it? The National Science Foundation put out a new fellowship program. Up until that time, research fellowships paid only around $2,000. This one paid $10,000, which was an enormous sum back in the early 50s. And Art Adams and I both applied, and we were both awarded it, the first awardees of the Senior Postdoctoral Fellowship from the National Science Foundation. I didn't use mine directly because Argonne said they'll pay my way. I don't have to take the $10,000. They would pay all my travel expenses, living expenses abroad. And so I went to work at the ETH in Zurich, Switzerland with Professor Schwarzenbach, who was inorganic chemist there.
So I guess you turned over the bioassay work to Jake Sedlick by then.
Well, the work I did there was inorganic, more inorganic, measuring complex ions.
No, I mean, what you left Argonne, so somebody has to take over the work there, the routine.
Yeah, I had a group there that took over. That was Marshall White Rosenthal and, well, that was later.
Lindenbaum.
And Arthur Lindenbaum, but that was later. When I was at the University of I met Lindenbaum at the University of Minnesota when I was assistant professor there for a year. That was in 1947 to 48. That's right, Lindenbaum was there. And anyway, so I left the group there, but Lindenbaum and Marshall White Rosenthal were the main people that kept it going. And we corresponded a lot. In the meantime, I started, well, in 1955, I was a delegate to the first conference called by Eisenhower, Atoms for Peace Conference. I gave a paper there. Maybe it starts in 90, I don't quite recall now. So many papers. A lot of papers I don't even list in my publication list, which were big papers.
Oh, you forgot to put it down, huh?
Well, I listed specifically. And then in '56, I went to Zurich, Switzerland to work with Professor Schwarzenbach and his group on using their techniques for measuring stability constants of complex ions. I worked mainly on iron and other. Spent a year there in Zurich, '56 to '57. Came back. And became an assistant professor later on. There were so many, it's very difficult for me to put them all together here. 47, 48, assistant professor of physiological chemistry, University of Minnesota, where I did a lot of work on carbon-14 metabolism, but I also did some fundamental work, which has applications even to the present time, CO2 in the atmosphere. I was working on measuring C14. There was a standard method of precipitating C14 labeled CO2 with barium carbonate, and then putting the solid on a disc and measuring it. And this department was headed by Armstrong, Wallace Armstrong. And when I came there, his graduate student was Arthur Lindenbaum, who was measuring C14 and was supposed to study that. But he never could measure the C14 because as he kept adding more barium carbonate, the counts kept going up and up. And you can't measure anything unless you have a uniform plateau. So I looked it over, and then I went over to Professor Armstrong. I said, I think I know what the problem is. As Arthur's adding more and more barium carbonate, you're getting closer to the window of the Geiger counter because he's adding so much. And I said, you know, the maximum absorption is only 20 milligrams per square centimeter. That's based on Libby's work. I should say I knew Libby quite well, too. And I'll never forget the reaction of Professor Armstrong. He looked at me when I told him that. Theory! He just barked it out. Theory. So anyway, I developed a method showing that as long as we stayed a little above 20 milligrams per centimeter, everything was nice and good.
A little above, or you say below? You mean just not going too high, you mean?
That's right. Just kept it very systematic amount.
Mm-hmm.
The method was very good. One thing I found, though, on the measurements, which is rather interesting, they have these samples of barium carbonate labeled with C14 to measure, and I put it in a desiccator, and I noticed the counts kept disappearing, and what was really going on? Well, it turned out, when I made a complete analysis, I put the barium carbonate, this gets in the desiccator over water, and then I would exhaust the atmosphere. And I found that the C14 and the solid barium carbonate was losing it to water. As a matter of fact, eventually all the carbon-14 would be gone. I quantitated making of it. And so I wrote a paper in Science with Professor Armstrong, showing the exchange of carbon dioxide with atmosphere and water and so on. Published that in Science. And I was amazed at that. While in Minnesota, Charles Coriel called me. They were setting up a program to measure the distribution of plutonium fission products in Bikini 1 year after the original bomb went off at Bikini in '46. And they wanted to know what happened to the fission products on the land and the water and in the water and the bottom of the bikini. And so he asked me to come out. And I said, well, gee, I don't even married for 3 months. I don't go out there, take a ship out there. So he said, well, I'll send my wife out to Hawaii while I'm in bikini. I said, well, my wife's sister, well, we'll send her out to Hawaii too. Well, I said, at that time, Hawaii wasn't that nice place to go. So I eventually flew out on the big Mars seaplane of Hughes and spent a month on the ship being involved in analyses of plutonium and fission products in the bikini, in the seawater, in the bottom, and elsewhere. I never published that work. And Larry Glendinning did more of the fission product, and I did the plutonium, but I also did some of the others. And I was able to predict, in a general way, from the known chemistry, which elements would be concentrated in the bottom of the bikini lagoon, which ones would be more in the seawater, things of that sort. It worked out very well. And I have a paper which I should publish on that. There are a few papers I should publish which are historical and of great interest.
There are always these leftover things to do, yeah.
This was sort of environmental chemistry at that time. And anyway, that was, I spent a year at Minnesota and then returned to Ireland. I don't know, this can go on, you know, I haven't even...
Yeah, let's take a break here a minute. Here we are again with Jack Schubert. And after another little break, we go on and on and on. We could go for many days, but we only have 2 hours of tape here today. But we do want to capture his wonderful career.
Well, thank you, anyway, actually after Minnesota, in 48 to 58, I was senior scientist in the Division of Biological Medical Research at Argonne after that I retired. And then in 59 to 60, I'm sorry, I'm reading this, I was an exchange professor at University of Chicago and University of Frankfurt. And then another time at the Max Planck Institute for Biophysics in Frankfurt at the same time. And so I worked on many things and lectured a lot of stuff around Frankfurt and Germany. Went to a lot of meetings around Germany.
You learned to speak German?
Yeah, I actually lectured in Germany. I gave it, at the University of Frankfurt, I gave a course on chelation chemistry. I delivered it in German. I learned German with a Swiss accent from getting more or less relatively fluent in German at Zurich, Switzerland.
Were they using chelation on humans at that time for removal of plutonium yet?
Well, actually, they were using it, but no one told me about it. Actually, at first I used zirconium compounds, which cleared the plutonium from the blood, but there were potential toxicology problems. I used zirconium citrate and published a paper showing that I was able to eliminate plutonium from the blood using zirconium citrate. And then I experimented with zirconium malate, and then without my knowledge, some medical people, I think mainly in England, were using zirconium malate on a human. And I think they affected the middle ear, which sometimes chemicals do. And they never consulted me about using that. I wouldn't have recommended the malate because it isn't as stable as the citrate. But anyway, and then I started using EDTA and that. Though the first person to use EDTA, I believe on humans, was Harry Foreman of Los Alamos.
I remember him, yeah.
And then I went
He was
over.
a medical doctor too, wasn't he?
Yes, Harry was a medical doctor. And then I graduated used DGPA, which is a better chelation. And I tested all those and measured the characteristics. I also also measured things with Marshall White Rosenthal and Arthur Lindenbaum. We published a whole slew of papers on it.
Yeah, I've seen some of those when I was with the whole body count.
We showed the difference between colloids, clearance of plutonium, and particle size, and the effect of chelation on function of time. I published a whole slew of papers on it. I published a few reviews as well, summarizing some of it.
I think you used some of that knowledge to advise us when Neil Wald was doing chelation.
That's right. When I
got involved with some of our
Pittsburgh.
patients.
Yeah, University of Pittsburgh,
Yes.
Professor of Radiation Chemistry, 65 to 77. Yeah, well,
Oh, and then you developed what we called Schubert's solution for
that's right. I developed
decontaminating people. I think we published that in one of our papers.
Yeah, that was.
We gave you credit for it, but we weren't an author on that paper. But we
for
called it
decontamination.
Yeah, it's in one of our papers. I think that Wald and I had published.
And I think they made barrels of it for use in industry at Westinghouse and elsewhere. It was a solution I made up to chelate, but also with calcium, so there wouldn't be any. It was a solution that was carefully balanced with a mixture of chelating agents and so
It
on.
worked very well on the skin of our patients.
Yes.
Who were contaminated with plutonium or
That's
americium.
right. That's why I put calcium in there, so it wouldn't irritate the skin. And yeah, we used it to decontaminate some of the people who got contaminated with plutonium, and there were some other accidents, I guess, a few minor accidents. Yeah, Schubert.
You whipped that up for us. You hadn't published that before, had you?
I never published it.
Just made it right up.
Published in, well, Neil Wald talked about it. He mentioned the thing and
Yeah.
put in the formula according to what I gave him.
We got that somewhere in one of my reprints.
Yeah, it's in one of Neil Wald's reprints, the Schubert solution, yeah. Well, I know it still uses a decontaminating agent. Or decontaminates the skin and
That's a paper you could give at the bioassay meeting.
Pardon?
That's something you could give at the bioassay meeting, a simple little paper like that, if you wanted to.
Well, it's a long time.
Put it on the record.
Anyway, before I came to University of Pittsburgh, I spent 3 years I was called to Argentina. What had happened, this was in 1961 to 64. The military was ousted from the government at that time, and the university was filled with professor appointments in chemistry and science by military people who weren't very competent in these fields, researching. So they wanted to set up a research. When the civilian government took over by Arturo Frondizi, who was the president, they wanted to set up a high-class research department there at Buenos Aires.
What year was that?
1961 to 64, a 3-year period.
That's after you'd argued with Libby, I guess, before Congress, was it? About the log novel distribution?
Oh, I can go in, that's another story.
That happened before that, didn't it?
Yeah,
Then when you came back, you got me involved in looking at that paper.
Yeah, I testified before a couple of AEC committees. And that's another story. And then I was involved in various UN IAEA symposia. But that's...
But you skipped the writing. You wrote that book with Lapp, Radiation,
I wrote
what it is and how it affects you. You wrote that before you went down there.
I wrote that book, finished it up mainly when I was in Zurich. And then I got in touch
That was in
with
the 50s yet, wasn't it?
Pardon?
That was still in the 50s, wasn't it?
Yes, that was in the 50s.
Yes, and it has been published in many languages. Here's a picture of one cover. And,
Japanese and...
yeah, I didn't bring them all down. I saw them upstairs. Here's copper and radiation biology, copper and peroxides in radiobiology and medicine, which was written later, I think. Here's a book, Nakod and Schubert, Ion Exchange Technology. And that was, you say you edited that?
Yes. I have an article in there.
You have an article. Here's a couple examples of the radiation book with Schubert and Lapp, and we've already interviewed Lapp. I mentioned this book. And here's it with a paper cover, and there are some also some paperback books upstairs of the same kind.
Yeah, they were in Spanish.
So,
There was a Spanish translation, the Dutch, Japanese.
so they kept republishing that.
Yes.
You must have had a lot of royalties on that book.
No, not many.
Not really. Didn't pay much royalty in those days, huh?
No.
But a lot of them were apparently printed, huh?
Well, of course, that book had an adverse effect in certain respects. The medical doctors and some people in the AC weren't happy with that book because it criticized certain
Yes, but in those days, there was still a little bit overuse of machines that were not properly filtered, and that the medical diagnostic doses were not optimum in those days.
No, but they overdid it anyway, especially with fluoroscopy, which was,
Yeah.
we could deliver as much as 50 rads to the fetus.
Mm.
You know, they like to show the mother, the
Yeah.
fetus, and the stomach and everything.
Mhm.
And you're delivering up to 50 rads.
Well, do you think your book had a good effect on reducing that?
I assume it had some.
I imagine it must have.
It must have had some. But
And the
anyway,
Public Health Service then had set up an organization, which later was under John Filforth, called the National Center for Radiological Health. It had other names. It's still in existence, so but John is retired and still very active, working for a legal foundation. You remember John Filforth?
a little bit. I didn't have much to do with it.
He supported some of our work at his group. He was a division chief, I think, then.
That was after I left.
No, Joe Filforth was there, but you didn't interact so much because I had intended to turn over that project for the second 3 years to you. I remember that.
Yeah.
And you just
Never
told me
reached-
that it never got to you. Near Wall took it over.
That's right.
But you were the expert, really, on chelation
I know,
therapy.
but remember.
And I wanted you to have that. But
Well, I was sometimes, depending on my views on fallout and other views, I was sometimes the fair-haired boy of the AC and other times persona non grata.
you were always, you have your honest opinion, though, didn't you?
I need my answer.
You're a good American.
And then when I testified before Congress on the NCRP, I pointed out that the committee wasn't qualified to pass on permissible levels at the time. This was in the congressional hearing. Not that the people weren't good, but they didn't have a representative of enough disciplines. They didn't have statistician or geochemist or things of that sort, people like that. And of course, that didn't sit well with the NCRP.
Although maybe your remarks echoed and had an effect in history, because now they have many more disciplines involved.
I know. But at that time,
I imagine Larson Taylor was not happy at that
if you
time.
read my paper, I think I actually published the paper pointing this out also in the, what was that magazine published in Chicago? Get the name of that. Again, I have to look. But I published a paper on that business and also on...
Bulletin of the Atomic Scientists, you mean?
Yes, Bulletin of Atomic, I think it's Bulletin of Atomic Science. More technical. But again, I'd have to go through over 160 publications. Remember, I also got into matter of fact, I published about 40 papers in the fields of pharmacology and toxicology. So I got into a lot of other areas.
Mm-hmm.
And as a matter of fact, I always like to apply chemistry, physical chemistry, and that to biological medical problems, which I do.
Yes, that's beautiful work.
So I think,
I wish I could begin to read some of your books.
yeah, well, our
Again,
papers,
some
of the papers are very interesting. I also spent visiting professor at the University of Stockholm in Sweden, dealing with environmental issues. As a matter of fact, I took part in the first Environmental Earth Day
When was that?
in Stockholm.
What year? Do you remember? Well,
It was about 52, you see.
1952. That long ago.
So wasn't that long?
Yeah. I would like to get up when you were chair of chemistry and you helped me put on the mid-year meeting on internal dosimetry back in 1983.
Yeah, I know.
We're a long way from there yet.
Well, I was the chairman of Gordon Research Conference in Ion Exchange 54, 55, delegate to the first international conference on peaceful use of atomic energy. Then I was a senior postdoctoral fellow at the NSF Zurich, and then Buenos Aires, consulted World Health Organization on irradiated foods.
That's what you were talking about before.
And,
very interested in seeing that come through.
yeah.
And maybe you just read off the titles of what you did. That would be
Yeah, I
nice.
think that's about all I can do. I hate to give a list, but it'll take us too long.
Maybe read off the titles of things you did.
Well, I'll
and
start
then we
at
go
the
back,
latest.
go back and pick up something.
I'll go with the latest and go backwards. In '93, I was visiting professor at the University of Hawaii at Manoa in Honolulu, Department of Environmental Chemistry. I lectured there.
In 93?
Several months.
Fairly recent.
And then I also...
That's after you retired from chairmanship of chemistry at University of Baltimore.
University of Maryland.
University of Maryland in Baltimore County.
That's right.
You were there, how long were you there at Baltimore?
Over there?
About. That's a major job, I think you had. Put it in perspective.
Oh yeah, from 1980 to 86, I was professor of chemistry and chairman emeritus at the University of Maryland, Baltimore County. And as I said, a visiting professor at the University of Hawaii environmental biochemistry. In 1988, I was a visiting professor at the Department of Food Science and Human Nutrition, where I dealt mainly with irradiated food chemistry.
Where was this?
University of Hawaii.
And that was for what, a year?
No, just 3 months.
3 months.
But I worked there with James Moy, who was involved on food irradiation.
Did some laboratory work?
Yeah, did some laboratory work. He was radiating all things like papayas and fruits. And so on.
You were analyzing what?
Well, I was trying to develop a method actually for determining whether food had been irradiated. So many experiences was a difficult thing. Made a little progress, but not too much. And then, well, I'll run through special appointments. I gave a short course of food irradiation at the symposium in Santa Barbara, California. I was dean of the summer school in '83 on courses on internal radiation dosimetry.
That's when we worked together and you helped us put that on for the Health Physics Society.
Yeah.
That was a very fun meeting. You had
And then at a
over
workshop
100
in
people
'82 at the American Institute of Biological Science. Then I was a lecturer at the short course on food irradiation update at the University of California. And then an IAEA FAO symposium on combination processes in food irradiation in Sri Lanka. And then I was director for a year in the Netherlands of a joint FAO-IAEA training course in food irradiation at the International Facility for Food Irradiation Technology in Wachameen in the Netherlands. And well, there I did a lot of worked with people in radiation chemistry, helped them on principles of radiation chemistry. Published a paper on radiation sewage, which enables sewage to be dewatered much more rapidly, and I showed mechanism involved OH radicals interacting with the surfaces of the sewage particles. And I published several papers there as well, documenting with students there. And then one of my students was a Dutch student, Jan Wilmer, who got his PhD with me. He published several papers with me. One of them I mentioned is hydrogen peroxide free in biological systems, which the demand for was well over 500 papers. showed that hydrogen peroxide really never exists free. It combines with amino acids, certain ones, and DNA and so on. And that's the way it was carried around. A particularly strong one with histidine. As a matter of fact, that was able to be crystallized. Hydrogen peroxide histidine adduct. Anyway, I wrote that in great detail in the paper. And Jan Wilmer, that was one of the papers as part of his thesis.
You were a professor where, when that was? When you had this graduate student? You were a professor overseas?
Let's see. No, this was, I'm trying to think when I was walking. I might have been at Argonne at the time, I'm not sure. But I took a year off.
When you were at Argonne, you had a joint faculty appointment
Yeah, but
at the University of Chicago.
yeah, I was a senior scientist, equivalent of professor, but when I was in Wageningen, I'm trying to think of, see, I was in Wageningen in 1976. The question is, 1976. There's a pit. I guess I took a year off when I went to Wageningen. Yeah, that's right. I was Professor Pitt. Anyway, so I can go on list and so on.
You were interested in many things for one person.
Yeah. And as a matter of fact, I published many papers, well, 40 papers actually, in the field of pharmacology and toxicology. I gave a course on that as well.
There would be many interesting things to talk about, huh?
Yeah, well, I can go into any one of them.
Maybe
They were great details, and also on radiation protection mechanisms.
Yeah. If you think we should do some more of this, we could do some more, you know? This is a nice general overview of your career, though.
Very general overview.
Very general overview of your career, and it's very good. And then maybe specific topics that you think that historically would be of interest and value to record would be also maybe some more.
Yeah, I have to think about it, but
yeah, you
have
have
to
time.
divide them into areas.
Right, yeah. Well, I hope you'll go on to do a lot more good work.
Well, I
You're
have several
still-
papers I have.
Still seem like a young man.
Yeah. Well, I'm just beginning my career, man.
You're only 83 and a half, is it?
Yes.
When's your birthday? Now you know it.
Oh, and I know my birthday.
When's
now.
your birthday?
September 14th,
September 14, what year?
1917.
Maybe I can remember it if I keep looking at
Let's
this.
see.
1917.
That's pretty close to my causing the entrance of the United States into World War II.
Well, then you're not 83. You're only 81 or something.
No, I mean, born in 17.
17? Oh, I see, yeah. I guess my math is not very good. Without my computer anymore, I'm lost.
You're not supposed to be good at that. Just equations. And of course, we did the work on log normal that I did.
Yeah.
That became a very important paper.
Yeah, I still have references. I want to show you some things.
Yeah.
I came up, I first met one of the main people doing work now on the Précis calculations for Senes. He came up to me when I first met him, and he knew me from that paper. He said that was a wonderful paper, and he's been using the log normal as a model for a lot of things in environmental work.
You know what got me into the log normal? I read in a general way, but Libby published 3 papers in the National Academy of Sciences on the distribution of strontium 90 and predicting the levels later on. And used a normal distribution, which I knew could not be, because the normal distribution came down, right down, which meant that the number of
You didn't get very high.
the number of people would have twice the average level, if you want to call it average, was a given number. There'd be practically nobody 3, 4, 5 times.
Yeah.
And so that's when I got into the log normal. There was actually a paper.
You
then-
saw a paper, and that's in our paper,
yeah,
where
but-
the log normal was very broad and very beautifully straight.
Yes.
on a probability versus log scale. We have that in our paper.
But what inspired me, there was actually a paper by a Norwegian chemist visiting here in Chicago.
Mm-hmm.
Published a paper, I think maybe on, might have been Transylvania, a short paper, and I think he used the log normal.
So that might be the one we have in there with very broad distribution.
No, that was a small paper. I don't know if
I mean, the distribution was very wide, so there were a lot of people. I can see why you'd be frightened.
Yes.
Be many people, more than 10 times the average.
That's right.
But we found out when we looked through the literature later that it kind of equilibrated around the world and it wasn't quite so broad.
That's right.
And then we found out, well, it's still worth using the log normal,
Well,
which later agreed with a lot of assumptions they were made legislatively.
Well, we were able to predict pretty much, levels. It worked out not only in that, but on many other things.
We have an estimate in our paper what fraction is 3 times the median.
I do have to locate two of the papers on the absorption, which are key papers in the development of absorption ion exchange on the Manhattan Project.
Uh-huh.
And it's one on the Bikini resurvey expedition where Glendon and I put out a paper which really environmental chemistry paper applying to plutonium and fission product distribution in the natural, in the ocean, and land and so on. So some of those I'll have to dig out.
Did you say you left Pitt in 77? Yeah.
Yes.
What did you do between 77 and 80 when you went to the University of Maryland?
I was professor of environmental sciences at Hope College in Holland, Michigan for 3 years.
For 3 years you were there. Did you teach undergraduate courses?
Yeah, I taught, I taught several courses. But I did mainly research, and I was still working on plutonium and other stuff at that time. And then I got a call to go to Maryland as a professor. And then a couple of years, and then they asked me to become chairman.
What did you do as chairman there?
I still do work, but administration jobs at the university.
Did you enjoy that?
That was pretty good, but it was difficult to do research as an administrator. But it was interesting.
And then you retired from there at what age?
Then I went to Michigan State University.
Michigan State, that was it. How old were you then? Let's see, that was
That was
1986, was it? 87, huh?
1986. I'm still adjunct professor in the Department of Biochemistry at Michigan State.
So you did some teaching there at Michigan?
No, I did mainly research.
Research.
Except for some isolated lectures.
Did you do some laboratory work? You had a laboratory?
Yes, I did do some laboratory work. As a matter of fact...
You work in somebody else's laboratory? Mainly? You were sort of retired then too, weren't you?
Yeah, but I worked...
Semi-retired.
Well, I did some of the work on... I worked with Assistant Professor Hollandwood on molecular studies using computer programs on structures. I was trying to elucidate the structures of the adducts with hydrogen peroxide and all that. And so we used a whole combination of physical techniques to do that. And I also did some radiation work. And also, a important paper came out of that. So I did several papers at...
I guess your daughters were pretty well grown by the time you went back to Michigan?
Oh, yeah.
Were they with you at Maryland when you were there? Were they still young then? Your daughters?
Let's see, I was
80, 87?
Yeah, they were grown up.
They were all still grown up.
Yeah, they were grown up.
Well, I've asked Jack to look through his curriculum vitae and just at least give some highlights of the very broad number of things that he's done that would have important applications through his career.
Okay, well, to save time, I'll read some of these off here. As far as fields of research, I worked in chemical, surface chemistry, ion exchange, micro and semi-micro analysis, stability constant complex ions, mixed laden complex, radio college, chemistry of fission products of plutonium separation processes, radiation chemistry and pulse radiolysis, catalytic decomposition of peroxides by metal chelates, and biological chelation, biology, medicine, radionuclide metabolism and removal, permissible levels of radiation, trace metal biochemistry and toxicology, medium effects in radiobiology, oxygen-carrying proteins, law of normal distribution, chemistry and biology of irradiated foods and food components, structure-activity relationships in microbial systems, mutagenicity testing, radiosensitization of enzymes and bacteria by radical anions, genotoxicity of combined effects, induced biosynthesis by bacteria of metal selective or specific chelation agents, channel biosynthesis, radiation protection, and then many of the course I've got. But here what I listed some of the research which I think were at the time.
Did you mention berbericum and beryllium?
I'll mention that here. Yeah, I didn't mention beryllium here, but I mentioned under metals, toxicology of metals.
And you published some of that in Scientific American, didn't you?
I published a big article there, but I published at least a half dozen articles on beryllium chemistry, reversal of its effects in animals, and enzyme effects, and so on, mechanisms, and why beryliosis would develop. I showed there that the effect of beryliosis, whether it became an active disease or not, is a function of the surface properties, depending how it's treated, high temperature or what. And so some would go in the lungs, but they would remove fast, washed out, or so on. And others were so impervious that it wouldn't have any effect, even though the particle size was the same, and they would remain in the lungs. They had no effect because the surface was so refractory. But there was an intermediate form, depending on the treatment of the beryllium powder, that would stay long enough to cause a diffusion of beryllium ions from the surface of the particle and damage the lungs. And that's, so I was able to show that. Anyway, some of the research accomplishments. I introduced ion exchange and absorption processes to the Manhattan Project for the separation and purification of plutonium and fission products from irradiated uranium. I have 7 patents dealing with that. And then methods based on ion exchange and an enzymatic procedure, actually, to measure stability constants of complex ions and chelates. And then new approaches to cation and anion exchange methods of separation of metals, including use of mixed solvents and conversions of cations to anion complexes so they can be absorbed on an anion exchange rather than a cation. That made for much refining separations. And then investigation of the role of radiocolloids in the radiochemistry of fission products and radioelement metabolism. I think those were the first investigations. And the first experimental evidence for the exchange of atmospheric carbon dioxide with insoluble carbonates. Then the application of the law of normal distribution involving deposition of fission products in humans and the environment. And that was a very important paper published with Alan Brodsky. And then elucidation of mechanism of radiation effects on the oxygen-carrying copper protein hemocyanin. And I worked on protocols for the combined mutagenic and toxicological testing of chemicals and drugs, including computer program using minimum number of test animals or organisms. I established the metabolism, metabolic disposition of monomeric and polymeric forms of radioelements and the response to chelation therapy. And I introduced the concept and applications of metal carrier compounds such as zirconium complexes to modify radioelement metabolism and decorporation. And the chemical principles and chemical calculation involved in removal of radioelements from animals by means of chelating agents. that was an interesting thing because I was able to show that you couldn't, chelating agents would not work particularly on removing radiostrontium from the animals because of competition from calcium and so on. And I showed that it just wouldn't work, even though there's a lot of work done on it.
Was that once it got in the bone or even from the blood?
Even from the blood.
Suppose you put in additional strontium, would something?
Well, but you see, strontium would have to compete with calcium. And calcium would minimize the strontium from being uptake, being taken up. I showed that by calculation.
Take it up, but how about elimination? Wouldn't it increase elimination?
No, it wouldn't do much elimination. I showed that by calculations and actual experiments.
Oh.
I published a couple of papers on
In
that.
other words, the strontium was more strongly bound to bone matrix than
Well,
calcium?
bone, once it's in the bone, you couldn't remove it.
But to begin with, it was taken up.
But even in the blood, you couldn't tie it up with chelating agents, even though these chelating agents theoretically were fine. Same way with lead. I was able to show that many of the agents that tried to remove lead wouldn't work, and some that would, by using the relative stability constants and so on.
Does an EDTA remove lead from the blood?
EDTA?
Yeah.
Well, EDTA, plutonium reacts so strongly with EDTA that the competition with calcium is minimal.
But how about lead, EDTA?
Lead depended on the lead. It wasn't too good. There are better agents than EDTA for that. Because you have to take into account more than just the chelating constants. You have to take into account the hydroxyl competition by hydroxide ions to form hydroxides inside of hydroxide. So to make a calculation required more than just knowing the stability constant. You had to take into account the pH, the competitions from the hydroxide ion, from calcium, and so on. When you did all that, the effect on lead isn't too great. Even though the chelate constant, you have to also know the profile of this pH versus stability of the complex ion. And you have to consider what is the stability at pH 7, more or less, of the blood. It's quite different from, say, at pH 3 or 4. And then at pH 7, you have competition with hydroxide ion from the proteins in the blood. So there are ways to make an estimate on it anyway. And then I mentioned, oh yeah, this was important, identification of cytotoxic and mutagenic compounds in a radiated sugar solution. We actually isolated, synthesized one of the sugars that was responsible. I didn't synthesize that one. I wish we had. It's a very important compound. It's a dehydration product of deoxyribose. I think it has a bearing also on the DNA mutagenicity. And super radiosensitization of bacteria by inorganic radical anion. One of the bacteria that's very resistant to radiation is called Deinococcus radiodurans. And I showed I can make that as radiosensitive as salmonella, even though it's considered one of the most radiation-resistant bacteria, by using a radical anion formed in the solution by adding, I think which, by adding bromide or chloride, radical anions which attack tyrosine would prevent the bacteria from repairing radiation damage. The reason for high radiation stability, resistance of radioduran is because it was able to repair so efficiently the damage to the DNA. But by inactivating tyrosine with the radical anion, more specifically, that prevented the cell from getting energy to repair. And then it was just as sensitive as any ordinary bacteria. I mentioned that. I still have the paper. That's another paper I haven't published yet, except I did give some information on it in one of my earlier papers. And then mechanism of action of ionizing radiation on conditioning with sewage sludge, showing that the mechanism by which you can remove water much easier from a radiated sludge and why. and how you can modify it. It's important if you want to do an economic removal treatment of sewage stuff. And then I did a, I think still an important paper, survival of lethally irradiated animals predicted from radio protection induced biochemical changes in non-irradiated animals. And then the application of Ames mutagenicity test to radiated vegetables. I did that in Hawaii because that's what they're working on, vegetables and fruit and so on. Anyway, gives you some idea.
Thank you very much, Jack. That's
You're welcome.
a nice trip around the world in science. Thank you very much. Now
There's
let's
a
go.
lot more, but meetings and paper.
Yeah. Now I'd like to, if we may, I'd like to walk around your home, beautiful home, and show some of the beautiful pictures you have, particularly the artwork of Mary, who is so excellent
an
an artist.
Are not married, but I'll tell you what they are.
But also Mary, because I'm really impressed with her ability to reproduce the human face like a photograph with even just watercolors. It's incredible.
Yeah, well, she was a master of all sorts of medium, from prints, portraits in different media, pen and ink, great pen and ink stuff, which I don't have up here.
Wonderful, beautiful, talented lady. So I'll shut this off now. That's Mary's work.
Yeah, that's a semi-abstract of sunset in winter over from our cottage in
Michigan?
In Port Sheldon, Michigan.
Oh, beautiful. Very imaginative. That's not Mary's.
No, this is an Argentine painter, Sanchez. These are pictures along what you call the pampas there. And here's another one by him. I call Sandstorm by Sanchez. He was a communist, but to make a living, he painted. I mean, he sold paints to make a living. And then this is the La Choza, which means little huts, by Sanchez. This I think is the best one.
What's that over there?
That's by Henry Kerner, very well-known artist. This is called the Eel Eaters. This was taken during the war, soup kitchens in London.
Ralph Lepp has a lot of paintings around too.
I know. Well,
this was given to you by Ralph Lepp from Japan. He has a lot of things like that.
He gave me those too.
All right.
Yeah, it's sort of symbolic of the wall.
The wall. Which?
I don't remember if that's exactly the name.
That's the wall in Berlin, huh?
Yes. Berlin.
Copper.
Right. Made from copper by Herbert Friedlander, a well-known Pittsburgh artist, but very well-known internationally. E-R-N-I, a Swiss artist. This was one of his earlier things when he had a Japanese influence, sort of. Very well-known artist. And this is a Spanish artist, which is obvious.
A beautiful large room here. Big kitchen.
And then we'll go in the other room here.
A lot of collection.
Yeah. I don't know if these posters may not mean anything.
Was Mary a big collector?
Well, you know, we traveled so much. We picked up things from everywhere. France, Argentina, name it, Denmark, Sweden, Italy.
I like interesting little things like that. This is a big, long kitchen.
Mary calls it a bowling alley.
Bowling
That's
alley.
what she called it.
A lot of room for this. That's from Italy? No,
Argentina.
Argentina. You were in Argentina. Then you got that, huh?
That's France.
France.
That's France. And this was exhibited at Carnegie Mellon University here in Pittsburgh. Picasso lines cuts.
That are sold?
Yeah.
Wow.
And this is
something.
A still life, one of Mary's still life that Mary made there.
I can zero in on that. Beautiful. Henry Kerner.
Yeah.
Which grandchild is that?
That's Kathy's, oh wait, no, that's my youngest daughter Amy's daughter,
Mm-hmm.
Lydia.
The eyes are beautiful.
Oh, yeah.
And this was done in watercolor by Mary?
I don't know if the watercolor, which yeah, that's a
And that's an original, huh?
Oh, these are all original.
Gosh, this is a later production. But who is that?
That's Lisa, the youngest daughter of my oldest daughter.
Mm-hmm. Kathy's youngest daughter, Lisa?
No, this is Kathy's oldest daughter,
Oh,
Eva.
Eva. How old is she now?
She's now just turned 12.
2001, huh? Oh, like our twin granddaughters are.
And
And then, wait a minute, I didn't get this one. On the other
Natalie,
side.
that's Kathy's youngest daughter, Natalie.
Beautiful.
And that's Ann's daughter, Julia.
How old is she now, do you know?
She's about 10 now.
And
This is my youngest daughter, Amy's son, John.
John. And that's who?
That's Thomas.
Thomas? And
Amy's
Amy's son. How old is he now?
He's now, I think he just turned 12.
12. Oh boy, what a family. Well, let's see.
And then this
Who is
is
she?
an early baby picture of Julia that Mary did. These are all originals by Mary.
And Julia is now what?
12 now.
12.
She was a baby.
And she's Kathy. Julia's Kathy's?
No, Julia is Ann's.
Ann's. Ann is here
The
in
oldest
town.
one.
Amy is away, isn't she? She's lives far
Amy's
apart.
in Seattle.
Seattle, Amy.
Oh,
That's
she's
marvelous. And these are almost like photographs. They really look like the kids, huh?
Well, Julia and her sister, the only grandchildren we have with brown eyes.
Huh.
And not only that, her eyes
But
are,
this is just a good replication if she had a photograph.
Yeah.
Mary was able to reproduce that well. That's incredible.
and she has slanty eyes like
Mhm.
Mary. Mary has somewhat slanty eyes.
Oh.
It's sort of a Norwegian thing.
Uh-huh. And that's Mary, your wife, when she was how old?
Well, when we first met, she was 19 at the time.
Looks like a movie star.
She was more beautiful than any movie star.
Did she ever
Never used makeup or anything.
Did she ever go into acting?
No.
Ever been on stage?
No. Her mother was, and her father was.
Was she shy?
No, it's just that she was more interested in academics and art
Uh-huh.
and history. Yeah, you have some music.
So-
You have musical ability. Now, I don't know. What do you want? You don't take all that stuff, do you?
What's that Hebrew?
I show that I climb Mount Zion.
Uh-huh. Is that hard to do, climb Mount Zion? No. It's not really that tall a mountain. Hmm? Here is the loft where I stayed last night. Very comfortable beds. Large room with a nice fan overhead. Slept soundly. Look at handsome Jack.
Oh, yeah.
A beautiful smile. That's about what you look like when we were in Pitt together, I think.
Mm-hmm.
You had a little bit more hair then, like I had a little bit more.
More hair. And it was darker.
Yeah. This camera's amazing. Even in the dark, it takes this picture beautifully.
I can put a light on here.
But look how it looks. Even in the dark, look at this. How it amplifies. Look at that screen. This is a self-portrait of Mary by Mary. Look at that.
Better be by Mary.
Perfect.
But you see, she makes herself sort of.
Yeah.
Never know she's so gorgeous.
Didn't want to smile.
Daughters don't
Very
like
serious.
this picture.
Very serious. I like it though. There's a photograph of Anne.
Yes,
She also lives not too far away. Hmm?
that's right.
Yeah. Oldest daughter. How old is she now, if you could say? About
She's just turned 50.
50. Lovely. Alonzo, huh?
It shows the woman covering her son.
Look at that dashing young man. Now, who's that? Movie actor? No, it's Jack Schubert. He's not in the movies yet. Except this movie right here.
That's right.
This is a first. Now here's a caricature Mary made of herself.
Yes.
Isn't that sweet?
Yeah.
And that's Jack in the Caribbean. Look at
Yes.
sport. Fishing? Do you fish?
Realtor. I don't know. She's put there just for me.
And who's that beautiful couple here?
That's my youngest daughter and her husband.
She's gorgeous. And he's handsome.
Oh, he's a very handsome guy.
Yeah, let me do a close-up on that.
He's a executive now at Boeing.
Oh, look at this close-up. Well, she could be a movie star. Does she sing?
She's very good at the piano. And this is Mary. Did this thing here.
Mary did that?
Yeah.
What is that in? The pen?
Yeah, it's pen and some coloring.
Oh, she's got her name at the bottom there.
Yeah.
Mary Schubert, look at that. This comes out beautifully in this camera. Oh, you'll see this when you get a copy. Mary didn't do that one. That's.
No, these are photographs of Anne's two children, Lisa and Julia.
Julia's the top one.
Yeah, the older one.
Beautiful. And those others are photographs.
That's Kathy's Natalie.
Different views of her, huh?
Yeah.
So cute. These are all originals of Mary's, huh? Here in the den downstairs.
Yeah, is that too dark?
It's a little dark, yeah.
What? Let me open the blind.
That's a nice portrait.
Yeah.
Not too many years ago.
No, not too much.
This is her bachelor's degree in art, huh?
Yeah. Then she has a master's in art history, which I haven't framed yet.
Where did she get that?
University of Chicago.
Yeah, great. This is Kathy.
Kathy Weiss.
Kathy Weiss, that's her name now.
Yeah.
And
And that's Amy Draxler, my youngest daughter in Seattle. D-R-A-X-L-E-R, Amy Draxler. That's Mary's sister Roseanne, who lives in Minneapolis.
looks like a lovely woman too, huh?
Yeah. And then that's the friend, our friends from Wales.
Mary
name's
did all
Caroline.
these. Mary did all these.
Yeah.
I
And
guess
then
people-
that's her father, Steve.
What's this little? Is that something?
That, I don't know who did that.
I can zero in on the author. Barbara or something?
Oh, yes. It was a very dear friend in Holland, Michigan, that Mary's. One of the few Jewish people living there. They're well-to-do. And she's a great lady. She died, unfortunately.
She was also an artist, huh?
Yes.
Now, who's this one here?
That's the father of Caroline here.
Father of Caroline.
Steve. Steve
Wow.
Alway.
Where was he from?
Wales. They live in Wales.
Oh,
They
you
were
were
our
you-
neighbors in Argentina.
Oh, I see.
That's how we got
That's
to
how
know.
you got to know
So
them.
we've been in touch for over many years.
Does she look a little like Mary? Half sister of Mary's, Dawn. Huh?
Yeah.
Is she still alive?
Yeah.
Where's she located?
Cape Cod.
Is that a black and white pencil?
Pardon?
That pencil?
I think it's pencil.
Charcoal, maybe?
Yeah, it's charcoal.
And up there was what?
That's an artist, a well-known artist, Herbert Olds, I believe. It shows a rabbi, I guess, or Jewish.
Well, here's a little picture of a little girl again.
Oh, that's Lisa.
Lisa, sweet Lisa. Now this is something
That's
of
Mary's
Mary's right
too.
there.
It's a print that Mary made.
What does that represent now?
Well, you know, this was a bank, and then this is abstract of,
Oh,
what's I'm not sure what. It's Johnny,
Johnny.
my youngest daughter's.
Look at this, watch this. See that on the screen? Look at that.
Isn't that great?
Look at that. They can put that on a large TV screen now.
Yeah.
Look at that one.
That's,
You'll figure it out later. You can figure it out later when you see it. You did that one from a model, huh?
Say,
This is the master bedroom, huh? And where is it? The one on the wall here?
yeah, that's Anne, the oldest daughter.
That's Anne. Wow. Another masterpiece. Wow, look at the clothing. You got all the details. It's so beautiful.
I mean,
I'm getting some reflection
Mary's
here.
technique, I mean, she was so gifted.
I'm getting reflections or something.
Her mother, her
Can you
grandfather.
turn a light on? I think I'm getting too much reflection.
Getting too much reflection?
Yeah, I need some light on the subject. That's better. Oops, now that's in there, the reflection of that. Is there another light in back, overall light in the room?
Yeah.
Overall room light?
Here, I'll put one here. I can turn this one on brighter.
These come out nicely. And there's a picture of you at the beach.
That's an herb.
How old were you're Uruguay?
Yeah.
Something writing on the top there. That's Mary, huh? When was that? That was when you were about 40?
1963, I think.
You were about 40-ish, huh?
1963. 45 or so.
Mm-hmm. And there's a nice picture of Mary right there. She's a little older. That's how I remember her. Right there. All right. I'll take a little bit of this. You can see it pretty well, right? But they're pretty. And these are some more pictures. What's it? Who's the name of the artist again? I just turned it on.
Carlos Alonso.
Carlos Alonso.
Very famous now.
Uh-huh.
And this, what it says in Spanish,
Yeah.
you can translate it two ways. It's a woman with something on her head or something on her mind.
Let's see.
You translate it either
Uh-huh.
way.
And who's that over there in that picture?
That's our youngest daughter, Amy, when she was only about 4 when we were living in Argentina.
Very pretty, very pretty. And this is a picture again of Mary, the one, like the one upstairs, huh?
That's the same.
And that's this one over here. This picture on the right. Is that Mary too?
Yeah, that was
This
less
is-
than 2 years ago.
This is Mary just less than 2 years ago. She's in her 70s then, huh?
Yeah.
Look at that beautiful
70.
smile. Look at that beautiful
Remember, she
smile.
had her Alzheimer's fairly advanced by then.
She could still smile,
But
huh?
even with our Alzheimer's.
Look at that. How sweet she was, huh?
Yeah.
That's a beautiful abstract. She did all kinds of things.
Oh, I have loads of stuff. This, you've only seen a small fraction of her work.
Oh, she got all this with Stuart, I guess. Huh?
She used to do very good jewelry out of plastic.
Wow.
She sold a lot of stuff. She'd sell everything she made.
Uh-huh.
And a lot of people have portraits. They
Uh-huh. She would be commissioned to do a portrait sometime.